In this video we're going to talk about some of the practical considerations for setting the bias point of common emitter amplifiers. By the end of the video we're going to identify a flexible and robust biasing technique that we'll use through most of the class. The most naive way to bias a common emitter amplifier is just to attach a voltage source directly to its base. If you do that, the only way to add a small signal input is to stack it on top of the biasing source, because two voltage sources in parallel actually gives you a kind of undefined solution since they can both pass infinite current. But stacking voltage sources like this is impractical in lab. Though you could make it happen if you had to, like with a battery or something. However, the real crucial issue with this biasing technique is that your bias point is exponentially sensitive to VBB. Because if you're just directly changing VBE here, then IC is approximately e to the VBE over phi th. So that's quite impractical for a variety of reasons. It would be really hard to make this work reliably or to get the same behavior each time you turned it on. Okay, so we can address the exponential dependence on VBB by adding a series resistor in line with the base here, which is the circuit we've been looking at for the past two lectures. That means we can calculate IB easily based on the voltage difference across RB, and then we can use beta to find IC. However, using beta to define your bias point is also fraud. Beta varies with the current level in your circuit and also with the temperature in the room, so your bias point will be unstable in this configuration. Also, we haven't fixed having the stacked voltage sources here, though. So there's more work to be done. However, before we do it, this circuit is a useful example of how to modify the common emitter amplifier property equations to account for your biasing network. So I've drawn this dashed line to show where the border of our amplifier is, and notice that our dashed line includes our bias circuit. It includes RB. So that means that a test source here would see RB in series with the R pi between the base and the emitter, making Rin increase. However, our voltage gain would be decreased, because before Vin is applied to the base here, it passes through a divider comprised of RB and R pi. So it's possible to add series base resistance to many amplifiers to increase the input resistance, but it's not a free ride. You often pay gain for it, and often you pay pretty dearly. So think carefully about the trade-offs if that's a design you want to make. R out is unchanged by the addition of base resistance, and that's usually true when you're accounting for the behavior of bias networks. So this kind of analysis is one that I'm going to ask you a bunch of questions on, because it's a easy way to get you to think about small signal modeling and the behavior of amplifiers, where we're going to modify standard common emitter behavior to account for biasing networks. We can fix our stacked voltage source problem by using AC coupling to connect a signal to the base, at AC but not at DC. Which is great. That problem was annoying. However, we're still relying on a series base resistor here to set our bias point, and so we're still haunted by the risk of IC changing as beta moves around. Using a series capacitor like this is AC coupling, and it depends on our input frequency being high enough that the capacitor has a small impedance compared to everything else in the circuit. But the input frequency also has to be low enough that hidden parasitic capacitors don't start causing our circuit's behavior to change. So that sweet region of frequencies where coupling caps look like shorts, but we're not haunted by high-frequency parasitics, is referred to the midband. And typically when we do small signal analysis, we will be making the midband assumption, which is that we can short out coupling capacitors. We'll figure out exactly where the midband assumption holds after our first midterm. once we start looking at dynamics. So this variation of the common emitter has an input impedance of R pi in parallel with RB, because we would draw the boundary of our amplifier to include our biasing network. And our base bias would be shorted in large signal analysis, leaving RB in parallel from the base to ground with R pi. Finally, we come to a biasing solution that avoids all the problems we've been complaining about in this video. We AC couple our input to avoid stacking voltage sources, but we're using a new technique to set our collector current. Instead of trying to set the base current and then letting beta determine the collector current, we're going to try to set our base voltage, which lets us calculate the collector current without using beta. The first step of this process is setting the base voltage, which we do with a voltage divider between R1 and R2. However, the voltage divider equation that I've cited up here only works when there's no current pulled out of the middle node of the divider, and the base draws some current in a BJT. Right, it's going to be equal to our collector current over beta. So we have to account for this base current in one of two ways when we're designing this type of bias network. The first way is just to make sure there's a lot of current running in R1 and R2, so that the base current is only a small fraction of it. And that's how we arrive at the inequality that I've specified at the top of the page. The other way is to do an exact calculation for the voltage, assuming that IB is being pulled out of the middle node of the divider. That's slightly more annoying math, but you can figure it out on your own, and you may have to do so in the next few labs. Once we know VB, we know that VE is just a diode drop below it, so it's equal to VB minus VBE on. We also know that VE has to be equal to the current out of the emitter running multiplied by RE. So VE is equal to IERE. And then conveniently, IC is about the same as IE because beta is high. So by picking R1, R2, and RE, we're able to set IC without depending on beta. Just as long as beta is big, we'll have a known bias point. However, our small signal analysis of the common emitter depended on the emitter being grounded. And we'd have to do a whole new analysis if the emitter wasn't grounded. So what we want to do is have our emitter appear grounded in the small signal analysis, and we do that by attaching a big capacitor between the emitter and ground. That shorts the emitter to ground at high frequencies. This works well, but again, it only works for a certain range of frequencies. We need this capacitor to be short at the frequency we're doing our analysis, but we don't want other parasitic capacitors kicking in. So this is just the mid-band assumption again, the same thing we rely on with AC coupling. The input resistance for this circuit is given by R1 and R2 in parallel with R pi, because all three of them are connected from the base to ground during our small signal analysis. R2 is just connected from the base to ground all the time. R1 is connected from the base to VCC, and VCC is shorted in small signal analysis. And R pi is connected from the base to the emitter, but the emitter is shorted to ground in small signal analysis because of the midband assumption. You may notice some tension between the desire to have a high Rin and the desire to have a lot of current running in our bias setting divider, because you want a small R1 and R2 to have a lot of current, but you want a big R1 and R2 to have a big Rin. And that's a drawback of this style of biasing. So in summary, there are lots of ways to bias BJT circuits. And a new fact that we learned is that depending on beta to set your bias point results in a really unstable bias. However, we learned a way to get around that, which we call resistor divider biasing, which involves putting a resistor divider on the base, which works best if the base current isn't large compared to the divider current. Otherwise you see some voltage droop at the base compared to what you'd calculate. And then we put a generation resistor on the emitter to set the emitter current. And then we short out that degeneration resistor at AC frequencies. So our small signal model is still a common emitter. The emitter appears grounded for small signals.